First of all, I'd like to thank the organizer for giving me the opportunity to present our recent work in uh, differentiating the various angular momentum in these magnetic heterostructure. For example, I'll be differentiating spin angular momentum and orbital angular momentum in NIPT heterostructure through terahertz emission spectroscopy. So before that, I'll be giving a brief introduction about the uniqueness of this terahertz emission, terahertz spectroscopy. So as you can see, terahertz lies in between, exactly between the electronics band and the photonics band in the electromagnetic spectrum. The frequency range that we are talking about is around 100 gigahertz to 30 terahertz, which correspond to this wavelength of 3 mm to 10 micron. And because of this frequency, it is falling in a low energy band. The typical energy that we are talking about in 1 terahertz is around 4 milli electron volt. So thermally, it will be around 48 Kelvin. And that's why it's a very low energy photon that we'll be using to probe the materials. Another thing about, another interesting thing about it is time scale, which is sub-picosecond in nature. So the resolution that we can have is in hundreds of femtosecond, right? That's why we can use this terahertz photon to probe many quasi-particles in various quantum materials, starting from excitons or Cooper pairs, electron acceleration. Most of the materials in nature we have, those have lattice vibration in terahertz frequency. So the phonon modes in those materials we can probe using terahertz frequency. And of course the magnons. So typically the 2D ferromagnets that we have been exploring till now, and most of the antiferromagnets, those magnons lie in this terahertz frequency, right? So this terahertz frequency is pretty interesting in spectroscopy point of view. So for that we do terahertz time domain spectroscopy, where we generate terahertz from these highly large Chi2 based nonlinear crystal zinc telluride emitter or gallium phosphide, or for higher power we use lithium niobate crystal. So what we do, we pump it with femtosecond laser. The femtosecond laser that we have is a 35 femtosecond laser with 1 kilohertz repetition rate. So we pump the emitter with this laser and we generate terahertz, and we put a sample that we want to explore in the focal point of this terahertz wave that we collect using this parabolic mirror. And for detection also we use similar zinc telluride detector, which is a high electro-optic coefficient material. That's why through electro-optic sampling, we can detect this terahertz that contains the information of the sample. Okay. So basically, this is a typical time domain terahertz pulse that we get, that we detect using this zinc telluride detector. And when we do fast Fourier transfer of this time domain pulse, we get this energy spectrum. And this energy spectrum actually contains both the amplitude and the phase of the terahertz that we are detecting. That means we can get the real part and the imaginary part of the dielectric constant directly without using Kramer-Kronik's rule. So that's why it's pretty efficient spectroscopy technique, and it's non-destructive and non-contact based spectroscopy, right? And these are all passive measurements. We can do active measurements as well. So we pump the sample at the exact same time when we are incidenting terahertz on the sample with 800 nanometer or 400 nanometer depending on the sample properties, and we can get the charge dynamics, the excitation and relaxation dynamics. And if we get the relaxation dynamics and the excitation dynamics like this, we get direct access to the various recombination process that we have in these materials. Currently, we are developing an terahertz pump terahertz probe spectroscopy, where we will replace this optical pump with the terahertz pump using a high power terahertz laser, high power terahertz source. And in that way, we can actually do this dynamics, charge dynamics in low band gap materials, for example, topological materials or graphene, something like that. Okay, these are all terahertz transmission measurement. We do terahertz emission measurement also. And there we get these magnetic heterostructure, where we can emit terahertz from these magnetic heterostructure, and we can get the information of spin dynamics and orbital dynamics from this magnetic heterostructure. And that's where the time scale of this terahertz becomes important, because the time scale of orbital and spin dynamics is in femtosecond time scale, right? So the resolution becomes important here. Instead of magnetic heterostructure also, we can get some, we can use some topological materials to generate terahertz, and that way it gives us information about the band structure also. Okay, now coming back to the main topic. So how do we generate terahertz using from these magnetic heterostructure is, for that we need to understand about superdiffusive spin transport. So what happens when we photoexcite the ferromagnet layer? So these magnetic heterostructure are basically ferromagnet and non-magnetic bilayer. So when we photoexcite a ferromagnetic material, what happens? These, because it's a ferromagnet, right? It has spin polarized electrons. So it extracts thermal energy from the laser fluence, and it tries to move away from this photoexcitation region. And now if we have a metal layer adjacent to it, it was believed till now that these spin polarized hot electrons will try to super diffuse into this adjacent metal layer. So what is super diffusion? It's basically an in-between transport between diffusive and ballistic. So it's not exactly completely diffusive and not exactly completely ballistic. So those spin polarized hot electrons will super diffuse into this adjacent metal layer. And if we replace this aluminum metal with a high spin orbit coupling material, for example platinum, then this spin polarized hot electrons, because of high spin orbit coupling of platinum, will scatter into opposite direction depending on what's the polarization and what's the spin Hall angle of this material. And then we create a imbalance of the charge. A transverse charge current we create. And this transverse charge current, because it's accelerated, we get an electromagnetic wave. And since everything is happening in hundreds of femtosecond time scale, the emitted electromagnetic wave will be in the terahertz time scale, in the terahertz frequency. So these are ultra thin materials, 3 nanometer each. So it's way beyond the penetration length of, let's say, the metals that we are using. So the typical length scale that we use in this heterostructure are around 2 to 3 nanometer each layer. Yeah, so we are beyond the penetration depth. Yes, correct. But again, these are ultra thin, right? So the temperature gradient will not be that much if we are talking about 3 nanometer. But yes, those Seebeck coefficient will also be coming into the picture. Okay. Now the benefits of these kind of emitters are, as I told him earlier, these are ultra thin materials, right? So typically the thickness is around 2 to 3 nanometer. The typical non-linear crystal based terahertz emitter that we are observing, those are in micron scale. So those have phonon modes in the exact terahertz frequency that we are talking about. But these are ultra thin materials, so there is no phonon, right? So we will get a gapless terahertz spectrum from, let's say, 0 to 30 terahertz. So this equation actually explains everything that I just told, all the phenomena that is happening, starting from absorption of the optical pump to the acceleration of charge current and hence terahertz. So there's an important term here which is called spin diffusion length. So this spin diffusion length is basically the length scale at which the spin current is penetrating into this platinum layer and is converting into charge current. And typically platinum has a spin diffusion length of 1.2 nanometer. So in a crude way, we can say that within this thickness or just beyond this thickness, whatever spin current is going into the platinum layer, it is already converted into charge current. It is already converted into terahertz within that thickness. That means if we are increasing the platinum thickness from here on, then there should not be any change in the arrival time of the terahertz or the shape of the terahertz. There will be just some absorption of the terahertz from the platinum layer. So that's what we observe when we have NiFe as a ferromagnet and platinum as a heavy metal. So when we change the platinum thickness, we didn't see any change in the arrival time of the terahertz or the shape of the terahertz. But when we replace NiFe with nickel and we change the thickness of the platinum layer, for example, let's say this is now x is equal to 3, we see this terahertz, everything is okay right now. But when we increase it, there's a slight delay in the emitted pulse. Again, when we increase it to 9 nanometer, there is further delay. And when we are increasing it to 18 nanometer, there is further delay. That means there is a different transport mechanism that is going on instead of spin transport. Because as we know, spin cannot travel this much distance into the platinum layer. So whatever transport mechanism that is going on here, it is able to move or travel at least till 18 nanometer experimentally that we have observed. So it's definitely not spin transport. So the first thing that came to our mind is orbital transport. So why orbital transport? Because as we know, the spins are getting scattered because of the high spin orbit coupling of platinum. but orbital will not be scattered because of the high spin orbit coupling of platinum. So to understand that why orbital transport is the main transport, we need to understand the various coupling of angular momentum in this solid. So we are talking about magnetic materials, right? So we'll have local magnetic moment. We're talking about electron transport. So we'll have spin and orbital both. And we're talking about a solid, so we'll have lattice. This spin angular momentum and orbital angular momentum of the electrons, they are coupled through spin orbit coupling. The local magnetic moment and the spin, they are coupled through exchange interaction. And this orbital angular momentum and this lattice, they are coupled through crystal field potential. Note that the spin and lattice, they are not directly coupled. So whatever electron phonon coupling is happening, it's happening depending on the orbital angular momentum. It is independent of spin angular momentum. So there is an efficient orbital lattice coupling, which is mediated by the crystal field potential. But the most important thing that is coming to our rescue is the spin and orbital, they are coupled through spin orbit coupling. So if we have spin angular momentum in a system, and if we have a high spin orbit coupling system, then we can have an indirect source of orbital angular momentum. So the direct source of ultra fast orbital angular momentum we don't have till now. And that's why the nickel is a very good orbital angular momentum source, because it is the highest spin orbit coupling ferromagnet in the periodic table. So that means whatever spin current we generate through ultra fast photoexcitation of nickel, some of the spin current will be converted into the orbital current, and that is maximum among all the ferromagnets. So in short, what is happening here? So when we are photoexciting nickel with ultra fast laser, we are creating spin current, as I explained earlier. But this, since nickel is a high spin orbit coupling ferromagnet, some of the spin current will be converted into orbital polarized current, and as expected, this spin current will super diffuse into the platinum layer, stop at 1.2 nanometer, convert into terahertz. But the orbital angular momentum, since they are not scattered by the spin orbit coupling of platinum, they can travel as long as they don't experience a broken inversion symmetry at the platinum air interface. So they can travel for 3 nanometer, they can travel for 6 nanometer, convert to terahertz, 9 nanometer, convert to terahertz, 18 nanometer, convert to terahertz, and that's why we see the delay. So we extracted this time delay over thickness, and we plotted it, and we saw that this delay over thickness is following a linear relation. That means whatever transport is happening of the orbital, it's not getting scattered, it's not getting accelerated. So it's a completely ballistic transport, at least till 18 nanometer experimentally. There is one more observation that we had is the pulse width of the emitted terahertz pulse is increasing as we are increasing the platinum thickness, which is observed here. And that is pretty obvious right now because the orbital transport is long range. So we will have higher angular dispersion of this orbital current. So some orbital current will go straight, reach the interface earlier. Some will go at an angle, reach the interface later. And that's why there will be a broadening of the emitted pulse. And this linear plot that we are getting, if we calculate the slope, then we are calculating the orbital current velocity. So for this particular fluence, we calculated the orbital current velocity to be 0.14 nanometer per femtosecond. And this fluence we are talking about is 191 microjoule per centimeter square, which is pretty low. Now what we did is we increased the laser fluence that we are inserting onto the ferromagnet, and we saw there is slight shift towards left in the emitted pulse. That means we are actually controlling the velocity of the orbital current that is happening here. So what we did, we calculated the slope at different fluences, and we saw that yes, the velocity of the orbital current from 191 microjoule per centimeter square to, let's say, 1270 microjoule per centimeter square. We calculated the slope, and we saw that the velocity is increasing from 0.14 nanometer per femtosecond to 0.18 nanometer per femtosecond. That means we are having a 30% increase in the orbital current velocity by increasing this laser fluence. And why is it happening in orbital transport and not spin transport? That lies in the angular momentum coupling that we are talking about. So what is happening is when we are increasing fluence into this orbital wave function, we are creating a non-equilibrium in this orbital wave function. And as we know, the orbital angular momentum and the lattice, they are coupled pretty efficiently. That means this non-equilibrium orbital wave function will try to have angular momentum exchange with the lattice, which is driven by the crystal field potential. That's why as we are increasing the fluence, we are increasing the angular momentum extraction to this orbital wave function, and hence we are increasing the velocity, and that can be probed or proved using this continuity equation. So in some, yeah, okay, sure. So in summary, what we are showing here is NIPT is a very famous magnetic heterostructure, and then we are showing that the terahertz emission from this NIPT heterostructure is majorly because of the long range ballistic orbital transport, and we can control this orbital transport velocity using just optical means. So there are three advantages over these kind of orbital transport based emitter over spin transport based emitter. One is, as I showed you, the transport of orbital is long range, so we can have information carrying over a long distance rather than spin transport. Second is we can control the velocity of this orbital current very easily through optical means, which we cannot do in spin. Third is, since orbital to charge conversion doesn't require spin orbit coupling, high spin orbit coupling metal, we have more metals to explore to design this heterostructure. So you can, if you are interested, you can go through this paper that published recently. I'd like to thank my supervisor, Prof. Ranjan Singh from NTU Singapore, our collaborators who provides us the sample. This is our group. Last but not the least, the funding agencies.
Thanks. So question here.
So this polarization depends on the magnetic field that we are applying, magnetization that we are applying, right? So the magnetization that we are applying is in plane. So our heterostructure is like this, and we apply magnetic field like this. Yeah, that depends on the magnetization of the. Okay, so we always require this magnetization or this magnetization. Okay, so the polarization that we will get is always at one direction. So to change the polarization, what we can do is change the laser polarization that we're applying. That we haven't tried. We are currently trying that, and we think that that might be some interesting results that we're going to get.
Any other question?
So I'm not familiar with the field, okay? So treat it as a basic question,
Yeah,
actually. Okay. So this looks to me like a case of optically induced orbital angular momentum.
Correct.
Or orbital angular polarization, basically,
Correct.
right?
Correct.
And you also said that the velocity is proportional to the fluence, basically.
Not proportional, but we can control the velocity through fluence.
So what is the scaling?
Sorry?
What is the scaling?
Okay, the scaling will depend. Okay, so there is, why there won't be any proper scaling is because when we are increasing the fluence, there is slight delay in the emitted pulse initially, and then there is a left shift. So this is called a critical fluence that we need to have the fluence increase the orbital current velocity. So there are some fluence in which at some thickness the orbital current is coming earlier, and at some thickness the orbital current is coming later. So the scaling is difficult in this case.
Okay, yeah, thank you. But at least at the minimum, it will be second order, like most optical effects.
Yes.
Any other question? Okay, so I have also a very quick question. So I'm also not aware of your field. So when you have a strong spin orbit coupling, so your spin and orbital both are coupled now.
Yes.
So now I can't define spin as a good quantum number. But you were defining this also at the same time. I can't define.
Okay, so
orbital quantum number is also not good.
No, orbital quantum number can be good if it's a non-equilibrium system. It's completely a non-equilibrium system right now.
I can have the total angular momentum quantum number. That is good.
Correct. But the what I am saying here is, so this is a spin orbit coupling material, right?
Yes.
So now you are correct that the orbital angular momentum and spin angular momentum, they are coupled properly, right? So there will be some spin current. I'm not denying that there will be some spin angular momentum.
My point
electrons.
Is that I cannot define the spin current properly here.
No, we cannot. Correct. Yeah. We cannot define the spin current properly. But whatever spin current is there, what I am telling is, even if we can't define, because the transport time scale is different for these two angular momentum, we can differentiate it in this platinum layer, because what I'm saying is the spin angular momentum will stop at certain thickness, which orbital angular momentum will not. So that's why we can differentiate this. Yes, the time scale that we can differentiate. And that's why the terahertz emission is pretty important, because we get this resolution of femtosecond time scale.
Okay, thank you. Okay, let us thank the speaker again. So we'll have a tea break now.